Hello everyone. My name is Rachel Lieberman, and I am the Forensic Marketing Manager at Shimadzu Scientific Instruments. Thank you for your interest in this forensic webinar. Today I will be speaking to you about toxicology screening of novel psychoactive substances in postmortem samples by tandem LC mass spectrometry. I do not want to belabor the history of novel psychoactive substances to a group that is already aware of their dangers. But taking one look at the Emerging Threat Report for 2019, it paints a clear picture as to why it is important to have fast, sensitive, and robust instrumentation for these types of compounds. Due to the illegal drug manufacturing process, it is becoming more difficult to identify novel psychoactive substances in a forensic environment simply because there are literally thousands of ways to manipulate a compound to make a completely new compound. Finding a standard to add to a spectral library is oftentimes the bottleneck in a drug confirmation. And once a drug is finally added to the library, that drug is typically no longer on the streets and has been replaced with a new analog. Take, for example, IMF, or illegally manufactured fentanyl. Those alone showed 6 fentanyl analogs emerge for the first time during the 2019 reporting period. This is even more apparent when we look at 3 emerging drugs from 2001 to 2019. This chart includes alprazolam, oxycodone, and fentanyl. We did not see an emergence of fentanyl until 2015 and saw the peak for oxycodone back in 2009, with a steady decline since then. Furthermore, we can see here that the drug landscape is constantly changing as we are seeing more fentanyl analogs emerging, and even beginning to see an increase in emerging benzodiazepines within the last year. As the drug landscape is constantly changing, we have to think of other ways to accurately screen and identify for these new NPSs. Traditionally, immunoassays, or GCFID and GC-mass spec, have been the most common screening techniques used in forensic toxicology. These 2 techniques have been widely accepted and used in the forensic community, but with the drug landscape changing rapidly, there's an immediate need to be able to quickly add and identify new compounds to a screening method. By using liquid chromatography mass spectrometry, one can achieve this goal. I'll be discussing these 2 LC-MS techniques in more depth in the next few slides. There are two ways to approach the ever-changing NPS market based on what is required by the user. Should one use a triple quadruple instrument, as shown here in the diagram on the top? Or is a quadruple time of flight a more suitable option, as shown in the bottom? It may not be as straightforward an answer as one might think. As shown here, the triple quadruples typically offer more sensitivity because multiple reaction monitoring can be employed to increase signal to noise. MRM analysis allows for one to select a precursor ion, and after collision-induced association by a set voltage, a series of product ions unique to that precursor are selected. This is what makes the triple quadruple most useful for sensitivity and quantitative analysis. But a triple quadruple is limited in its mass resolution capabilities. Therefore, this technique is more widely used for known and targeted compounds. Although, utilizing the various scanning techniques, such as neutral loss scanning and precursor ion scanning, one can also offer tentative information for an unknown substance. A time of flight, or QTOF, is the more common mass analyzer utilized for true unknown identification. This type of mass analyzer provides better mass accuracy and offers a higher resolution that is not provided by a quadruple. One typically gives up some sensitivity for higher resolution, and if you want better sensitivity, then you give up the mass resolution. There's a compromise between the 2 techniques. For this presentation, I will speak about the benefits of QTOF in a forensic laboratory. Just to reiterate the previous slide, a time of flight distinguishes itself from a quadruple because it can provide higher resolution. But what exactly does that mean, and why is it important? Take, for example, these insecticides, alethrin and clethodim. These 2 peaks will most likely coalute in a quadruple, which has a unit resolution, as represented by the chromatogram on the top right and in the green spectrum on the bottom. But when you use a high-resolution instrument, such as a TOF, the interferences are minimized and the peaks are fully resolved. Saying it in a different way, unit resolution could provide a wrong mass measurement if peaks are not fully resolved. Now let's look at mass accuracy. So when we look at alpha-hydroxyatazolam and alpha-hydroxytriazolam, one can see how similar their masses are. If using a triple quadruple for analysis, These compounds may collote if not chromatographically separated. But when using the accurate mass, one would be able to look at either drug without the interference from the other using tighter part per million windows. As an example of the importance of mass accuracy, if I were to type in the mass obtained from a quadrupole for alpha-hydroxyatazolam, which is 359.07, into an online molecular search engine, 105 different elemental possibilities would appear. But if I typed in 359.07279, that number would be dropped down to a more manageable 13 possibilities. This number could even be honed down further if using MSMS data. The Shimadzu LC-MS 9030 QTOF mass spectrometer has 5 different data acquisition modes, with a TOF mass range of mass to charge 10 to 40,000, and the mass resolution is greater than 30,000 at full width half max at mass to charge 1972. The mass accuracy stability is better than 1 parts per million at mass to charge 622.5662 for over 24 hours. The max acquisition rate is 100 Hz. We will go into details of the 5 data acquisition methods in the next few slides. The first acquisition mode is an MS1 scan, whose chromatograms, or extracted ion chromatograms, can be used for quantitative purposes. The accurate mass XIC and retention time matching provide an unambiguous identification. An MSMS scan event, which is similar to the product ion scans in a triple quadrupole, can be used to create a spectral library, which can be used as a third qualifier for confirmation. Using a collision energy spread in an MSMS scan on the QTOF can provide a more representative tandem mass spectra than just a fixed CE acquisition, which is commonly used in the triple quad. These next 2 acquisition modes are slightly more complex, but can be extremely informative if set up correctly, especially when using and screening for unknowns. In data-dependent analysis, a survey event is scanned for precursors, and when predetermined parameters are met, a secondary MSMS event is triggered for the selected precursor. In this example shown here, we have one MS1 survey event, shown in black, that resulted in 5 triggered MSMS events as shown by the colored peaks below. Analytes of low abundance sometimes have a difficult time being selected in DDA analysis. Also, analytes can be triggered across multiple time points, creating an MSMS event with higher noise or fragments not necessarily from that precursor. This is shown in the pink traces here. Or a specific analyte will not be selected at all, producing no MSMS event for the analyte of interest. Exclusion lists are typically used in data-dependent analysis approaches to limit this phenomenon. In data-independent acquisition, or DIA, a survey event is scanned for precursors and sequential stepwise MSMS events are acquired unrelated to the MS1 survey event. As shown in this example, there are multiple MSMS events that are created by a smaller mass to charge step width. This particular approach allows one to provide a more complete picture of the fragmentation patterns for each analyte. Now that we've gone over the background, let's move on to the fun stuff. First to be discussed is an ongoing project using the Shimadzu 9030 QTOF for library creation of fentanyl analogs. A reverse phase gradient was created using the LC parameters shown here. The 9030 offers an accumulation option where packets of ions are accumulated in the collision cell and then synchronized with the pusher so the maximum amounts of ions will reach the detector to maximize the sensitivity. That was utilized in this particular example. Here's an example of the data using the previously listed LC-MS method parameters. A human plasma sample was fortified with a QC mixture containing 23 fentanyl analogs at 50 nanograms per ml. The sample prep was essentially a protein precipitation with cold acetonitrile with an additional dry down step, followed by reconstitution with mobile phases A and B. The green trace on the top chromatogram shows the MS1 scan with the extracted fentanyl analogs shown below. The bottom chromatogram shows a zoomed-in view of the XICs of all 23 fentanyl analogs. As you can see, the signal to noise is high enough in this example where this concentration could be drastically lowered in the future. In addition, the LC method was lengthened for isobaric separation purposes. To help increase the reporting confidence using the LCMS 9030, Insight Explorer software was utilized in this analysis for data processing. This is an example of the QC mixture. An automated library searching function generates a library score in addition to an ion ratio confirmation and mass accuracy tolerances in the software. The provided postmortem sample was subjected to the same sample preparation as a QC sample. Using the extracted ion chromatograms, a peak was seen at retention time 6.236. When scanned across the peak, there was a spectral library match to acetyl fentanyl. And the formula in the Insight Explorer software was also predicted to that elemental composition to be C21H26 N2O as more added assurance. Here's the data from a second postmortem sample provided by the collaborator. When initially looking at the extracted ion chromatograms of the 23 fentanyl analogs, a peak did not present itself. However, a strong peak was discovered using Insight Explorer's analyze algorithm. This particular peak had an accurate mass of 369.2335. The analyze algorithm searches a QTOF data file using overlapping spectral windows, finds the same ions in neighboring windows, and then considers it a peak, automatically. If we zoom in on the results, one can see a match at the appropriate retention time with a given predicted formula. When 369.2335 was input into the formula predictor, 3 possible elemental combinations produced themselves. The top contender matched the elemental formula for para-fluoroisobutyrylfentanyl, or its isomer, para-fluorobutyrylfentanyl. A standard for this analog was not provided, so I could not perform an exact library search. However, this did match the finding of the medical examiner report for this sample. In addition, Insight Explorer's Assign feature can be used to help accelerate unknown identification and compound verification workflows. In this example, the identification of fentanyl was verified by submitting the precursor master charge value to ChemSpider and checking the product ion spectra were in agreement and consistent with the parent structure. Searching with ChemSpider and PubChem are supported in the Insight software functions. Unfortunately, fentanyl is not the only drug being altered to create new drugs. Staying current with the new synthetic cannabinoids poses the same issue for forensic laboratories as IMF. As shown in the same DEA report for 2019, there were 5 new synthetic cannabinoids that emerged in the past year. This can be further visualized by looking at each synthetic cannabinoid graphically. We can see that AM2201, which was one of the original synthetic cannabinoids shown up back in 2012, is no longer being seen, and we have the emergence of 5-FADB and FUB-AMB over the last few years. With the increase in medical cannabis use and legalization of industrial hemp, there's been a resurgence in these synthetic cannabinoids showing up in CBD or THC-only products. Since there is not universal testing for all the CBD products on the market, there's been an increase in these synthetic cannabinoids showing up in these products. It is important for testing and screening to be performed for any cannabis or hemp product that could potentially be placed on the market. In this example, blood samples from postmortem cases were prepared by Miami-Dade Medical Examiner's Toxicology Laboratory and were sent to Shimatsu for analysis on the LCMS 9030. Using Cayman standards of 350 designer cannabinoids, a spectral library was first created on the 9030 QTOF. As new emerging drugs are identified, they can be easily added to the existing library databases in the software. An LC method, as shown here, was developed for sample analysis, followed by scan and data-dependent events in the mass spectrometer. Shown here is the chromatogram for the 350 synthetic cannabinoid QC standard sample. Formula prediction was done on the feature at master charge 364.20371, which initially matched to 910 structures. The product ion MS2 spectrum showed the presence of an indazole core group at fragment 117, while fragment 318 showed the loss of the COOH group. These pieces of information narrowed down the number of hits to 5 structures. The only structure consistent with the full MS2 pattern was the 5F80B metabolite 7. An extracted unknown postmortem sample was analyzed using the previous LCMS parameters on the 9030. A pronounced peak was identified here, around 3.9 minutes. When comparing to an authentic standard, two different synthetic cannabinoids presented themselves as possible matches, as shown here based off of the accurate mass and retention time. 5-fluoro-PY pica and 5-fluoro-CY-P pica. When looking at the assignment of the fragments for these two compounds, 98.0600 and 206.1340 were seen. Now, in theory, either structure could produce either ion of this mass to charge 98.0600 or 206.1340, but the MS2 library spectrum is needed to show which fragment is actually observed. In this case, it's the 5F-PY pica that is present. This is also matching what was found from the collaborator. So, in conclusion, the LCMS 9030 QTOF offers a solution to the ever-changing drug arena with its speed, mass accuracy, sensitivity, and resolution. Accurate mass, along with retention time and MS2 spectra, can provide identification confidence with screening using the QTOF. Having a high-resolution, easy amended spectral library match is the ideal workflow in the forensic world that requires little method optimization. And lastly, the analysis of true unknowns can be performed with high-resolution accurate mass measurement and Insight Explorer software. I would like to thank the toxicologists at both Tarrant County Medical Examiner and Miami-Dade Medical Examiners for providing the postmortem samples for these studies. In addition, I need to acknowledge the scientists at Shimadzu that actually performed this analysis. Sarah Olive is working on the fentanyl analysis, and Jeff Dahl and members of the LCMS product group worked on the synthetic cannabinoids method. Thank you for your attention during this webinar. My contact information is listed here, and if you want to learn more about Shimadzu's solution for forensic science, please visit our website at www.investigateyourlab.com.